Any questions about this before we move on to the last example? Okay. Okay, so the last one is one of these ones where we're measuring displacement and distance travel. And so if you remember, put this around. I won't bump it. Anyways, if you remember, when you were measuring displacement, when you're measuring sort of the change in position between the beginning and the end of a period of time, you're doing the integral of the velocity function. If you're ever measuring the change in something, you're always integrating the derivative. In this case, the derivative is the velocity function. So for measuring displacement, what we have to do is we have to integrate the velocity function. Now here, we're talking about this interval of time from 1 to 6. So I've got to put limits of integration are going to be 1 and 6. So here the velocity function is t squared minus 2t minus 8. And if we want to find antiderivative of t squared, it's going to be t cubed over 3. Antiderivative of 2t is just going to be t squared. Antiderivative of 8 is going to be 8t. And we've got to do this whole thing from 1 to 6. By the way, you'll notice some people, instead of the vertical bar, use a big square bracket like this. There are two ways of writing the same thing. I think the book tends to use square brackets most of the time. Anyways. So I'm switching back and forth just to show you that they both happen and they both mean the same thing. And either is perfectly fine as long as you're writing it out. Okay, so we've got to plug in 6. We have 6 cubed over 3 minus 6 squared minus 8 times 6. And if we plug in 1, we have 1 cubed over 3 minus 1 squared minus 8 times 1. Okay. So 6 cubed, I believe, is 216. Divide that by 3, you get 72. 6 squared is 36. So 72 minus 36 is 36. 8 times 6 is 48. 36 minus 48 is negative 12. Here, 1 cubed over 3 is a third. Minus 1 minus 8 is a third minus 9. 9 is 27 thirds. So this is negative 26 over 3. This is negative 12 is a negative 36 over 3 plus 26 over 3 gives you negative 10 over 3. So the displacement here is negative 10 over 3. So you've got 10 over 3 in the negative direction. Now again, there's some situations in which displacement isn't that useful a situation. One situation is, for example, if you drive from like Abbotsford to Vancouver and back, and you say, oh look, I haven't made any displacement, I'm just back where I started, this means I haven't put any miles on the car, right? The answer is no, of course. You put miles on the car when you've done that driving. And what the odometer reads on the car is not the displacement, not the difference between where you ended up and where you started, but the distance traveled, right? If you go one way and then you come back, again, the odometer in your car doesn't measure negative numbers, right? You'll never have, like, you can't drive backwards and make the odometer read negative. I mean, unless it's a really weird car that's built that way, then when you reverse it goes backwards, but that would be really weird. Yeah, anyways. Yeah, you have to mess with the car to do that. Anyways, so when you're measuring the distance traveled, the idea is both velocity in one direction and the other direction are both going to have to count positively. So to measure distance traveled, we're going to have a look at that velocity graph and see what the velocity graph looks like. Well, this velocity graph, it starts at negative 8, it goes down a little bit, and it comes back up, and it will cross, it crosses the x-axis at time 4, and then goes up like this. That's what the velocity graph looks like in this situation. Again, you're totally free to use your graphing calculator to come up with this graph. You will have access to your graphing calculator in the test. I mean, if you want to, like, use things like the vertex formula, figure out where the vertex of the parabola is, sketch the graph by hand, you can, but I'd recommend that you use your graphing calculator. It'll save you a lot of time. So the key thing is that this is the velocity graph. Now again, this part of the velocity graph is negative. If we want to measure displacement, what we've got to do is we've got to take this negative part of the graph and flip it up to make it positive, so that both the backwards traveling and the forwards traveling both count positively. So when we flip it up, the graph will look like this blue graph. This blue graph is the absolute value of the velocity function. And that blue graph is the one we want to integrate. This part of the blue graph is going to be the negative of the velocity function. This part that's been flipped, to flip something vertically, you put a negative sign in front. This part of the blue graph is the same as the velocity function. So, when we're trying to calculate the distance traveled, we have to integrate the absolute value of the velocity function. These are supposed to be vertical bars. Those are supposed to be brackets. And again, we're going from time 1 to time 6. And the idea is...
4, right?
No, actually, we're still measuring the distance traveled between here and here. We're going to split it up into 2 integrals.
Okay.
I
thought that's what you were doing.
Yeah, no, I was going to say, here it's telling you that we're measuring the distance traveled and the displacement over this time interval. Eventually, yes. Eventually, yes, I'll have to do that. But not quite yet. Sometimes I'll ask you just write out a formula which will represent the distance traveled. In that case, just write out this thing. You don't have to actually split it up into 2 separate integrals until I want you to actually calculate what the distance traveled is. So then we think, okay, so we're measuring from 1 to 6, the distance traveled. From 1 to 4, we're using this negative function. And from 4 to 6, we're using this positive. We're using the flipped function. From 4 to 6, we're using the non-flipped one. So we're going to have the integral from 1 to 4 of this guy plus the integral from 4 to 6 of the normal guy. Okay. So if we integrate the flipped guy, we'll get the negative of b cubed over 3 minus t squared minus 8t from 1 to 4. And when we integrate this guy, we'll just get the normal. Why am I writing v here? This should be a t. Oh, because I wrote a v up here, and that should also be a t. There we go. Yeah, v squared would mean I'm squaring the velocity. And I'm not. I'm just, the velocity is the, here we go. These are also supposed to be t's. I don't know how that happened, other than I guess what I was probably doing was I was probably thinking, oh, this thing is the negative of the velocity function. It's the flipped version of the velocity function. So I put negative v in first, and then I replaced the v with this thing and forgot to take out the v. Anyways, so here, this one is t cubed over 3 minus t squared minus 8t. And this goes from 4 to 6. So then I've got to plug in 4 into this guy. So if I plug in 4 cubed is, 4 times 4 is 16. Yeah, 64. 4 squared is 16. 8 times 4 is 32. Minus negative, I plug in 1, I get 1/3 minus 1 minus 8. Plus, here I'm going to plug in 6. I get 6 cubed over 3, I already said was 72. 6 squared is 36. 6 times 8 is 48. Minus, the last thing I'm going to do is I'm going to plug in 4, which gives you the same thing as I got here. No, same thing as I got up there. 64. Here, I'm just going to write it one line down. 64 over 3 minus 16 minus 32. So now, again, this is one of these ones. A lot of the time, these sort of distance calculations, they'll have sort of fairly ugly fractions in them. Again, if you've got your calculator, you shouldn't have a problem with this part. And again, if you make a calculator mistake, you can move that 9 out of 10 or 4 out of 5. It's not gonna, yeah. Calculator mistakes at this point don't take off that many marks. So here is a 64 over 3 minus 48. 48 is 144 over 3. So 64 minus 144 is negative 80 over 3. That's what the first thing gives you. This one, 1/3 minus 1 minus 8 is negative 26 over 3. Yeah. This one, 72 minus 36 minus 48 is negative 12. Why am I? Oh, the first one should be positive. Yes, because it's negative, negative. There's 2 negative signs here. This will give you a negative number. Then you make it positive. And the last one, the same thing will happen. This will give you the same negative number, but this negative sign will make it positive into another positive 80 over 3. So 80 plus 80 is 160, minus 26 is 134. 12 over 3 is 36. So 12 is 36 over 3. 134 minus 36 is 98. So that is the distance traveled. Again, often some of these problems end up having fairly lengthy calculations at the end. Hopefully that won't cause too many problems, but I just want to mention that, yeah. Okay. Any other questions about this example? If I ask you for something like this on a test or assignment or whatever, I'm going to ask you something a little bit easier than this guy. As you know, this problem took me 10 minutes, more than 10 minutes to do on the board. Just the distance traveled part took me 10 minutes. The displacement part took me, another 2 or 3 minutes. So I'm not going to give you a question that takes 10 minutes on the test unless it's something that's testing multiple topics in the course. So if you had to see something like this in the test, likely there won't be a t-squared in here. Or if it's a t-squared, it'll just be t-squared plus 1. It'll be, or even just t-squared. Like the formula will be simpler to make these calculations all a lot simpler. Any other questions about this? Great. Okay. So next I'm going to move on to doing muddiest point. Again, the only muddiest point cards I got last class were ones for those group problems I just went over. Since I've gone over those group problems, I don't have anything else from last class. But I did have one from the previous class saying, please do another example of evaluating integrals using limits of even sums. This thing they call the method of exhaustion. Doing it by sort of writing out the sum using some formulas, simplifying it the hard way. Just to mention, on the written assignment I'm giving out today, there will be one problem that asks you to do that. It's a written assignment, so you have all weekend to work on it if you want. And again, you have access to your textbooks. You can look up any of the formulas you need in there. So here's an example of an integral that we can integrate by writing it as a limit of Riemann sums. So the first thing to mention is we've got to transform this integral into a limit of Riemann sums, right? And the rule is we replace the integral sign with the limit as n goes to infinity of the sum I equals 1 to n. Xi squared plus 1, x squared plus 1 becomes xi squared plus 1, and dx becomes delta x. Right, that's sort of the rule for how you take an integral, you transform it into Riemann sum. The integral sign is the limit of a sum. X becomes xi, dx becomes delta x. So now we need to figure out, okay, what is xi? What is delta x in this case? Well, delta x is always b minus a over n. Here b is 4, a is 0. So that means delta x is 4 over n. Xi is always a plus I times delta x. The A is the place we're starting, which is 0. Delta x is 4 over n. So xi is just going to be 4I over n. So using those formulas, this integral will become, the limit as n goes to infinity, sum I equals 1 to n. Xi will become 4I over n. So we're going to have 4I over n squared plus 1. And that whole thing is being multiplied by delta x, which is 4 over n. So I'm going to simplify this a little bit. 4I over n squared is 16I squared over n squared. Multiply both those things by 4 over n. So 16I squared over n squared will become 64I squared over n cubed. Um, 1 times 4 over n will become 4 over n. And then because we have a sum of something plus something else, we can split up those two sums. We're going to have the sum I equals 1 to n of the first guy plus the sum I equals 1 to n of the second guy. And again, those are just using, actually, everything I've done from step 1 here to step 3 here, that's just algebra. That's just simplifying that thing inside the summation symbol. From step 3 to step 4, I'm using one of those properties of summation that I wrote down in the notes, saying that if we're adding together this thing plus this thing, same thing as adding together the first thing plus adding together the second thing. It's basically the same property as this. I don't know if you remember this. If I have an integral of x squared plus x, I can integrate the x squared, and I can integrate the x separately. It's basically the same thing that's going on here. So, the next step is to look at these two things and try to figure out what they are. Well, the key thing is that what this sum is saying is that for every rectangle, I'm going to add 64 times the number of the rectangle squared divided by the number of rectangles cubed. The key thing is the number of rectangles is not going to change from the first rectangle to the second rectangle to the third rectangle to the fourth rectangle. 64 is also not going to change. So 64 and n cubed both do not depend upon what I is. They're basically constants. They're fixed they're the same for every single rectangle. So those numbers I can pull out front of the summation sign. This part, when we're adding from I equals 1 to n of 4 over n, the idea is 4 over n is the same for every rectangle. There's no I in this formula, which means it's the same first rectangle, same for the second, same for the third, same for the fourth. So if we're doing this for n rectangles, what we're going to do is just going to multiply the number by n. Right? So we're having 4 over n for the first rectangle, 4 over n for the second, 4 over n for the third, 4 over n for the fourth. There's n rectangles, because this thing represents sum I equals 1 to n, this thing we're adding together for n rectangles. So we're just going to multiply this whole thing by n. We're adding something together for every rectangle, and there's n rectangles, we can just multiply that thing by n. If it's the same for every rectangle, this one is. So, the next step is to note that we have a formula for this guy, sum I equals 1 to n of I squared. I gave you it as a hint. Again, if I was going to ask you something like this on a test or whatever, I would tell you this formula. I wouldn't expect you to memorize it. So here, this formula says that thing gives you n times n plus 1 times 2n plus 1 all over 6. And this 4 over n times n is just 4. So now let's simplify this guy. We have an n on the top and an n on the bottom. Those guys will cancel. We have a 64 over 6. I'm just going to write that as a fraction. Here, if I expand that, it's going to be 2n squared plus 3n plus 1. And again, we've got an n squared on the bottom. Now here we're taking a limit as n goes to infinity of a fraction. And if you remember, when you take the limits of, we take a limit as x goes to infinity or as n goes to infinity, all the terms except the highest power are going to become insignificant. Right? The 3n and the 1 are going to become insignificant. So this whole thing here is going to go to 2. You'll have a 2n squared on the top, you'll have an n squared on the bottom. So 64 over 6 times 2 gives you 64 over 3. And then I've just got to add 4 to it. 4 is the same thing as 12 over 3, so the whole thing is 76 over 3. That's what this integral will give you. Now again, this is the hard way of doing the integral. I could have gotten that same answer by just using fundamental theorem of calculus, doing, x cubed over 3 plus x, plugging in the limits of integration. I would have gotten the same answer. And we've got exactly the same answer from the easier method. So again, this method is sort of the long and hard way of doing it. The only reason I teach this is for you to appreciate how hard this sort of problem was to do before people invented calculus. That's the sort of idea. But like, yeah, this is how people did things up until about 1600. When, yes?
Are we going to be forced to have like a test or quiz?
Probably not. Probably, I think the assignment that I'm giving today, the written assignment, is the only place I'm actually asking for you to do this. What I would like you to be able to do for a test is go this far. Be able to transform this thing into this thing. Be able to sort of interpret this as a limit of a sum. Actually going through the process of evaluating it, that's probably not something I'm going to ask on the test.
Would that be on midterms or finals?
That would be the test on midterms. So, the same thing for the final. Anything that's not going to be on midterms is not going to be on the final. Well, everything that's not going to be on midterms is not going to be on the final unless it's because it's material that was covered after the last midterm. That's the only reason there would be stuff in the final that wouldn't be on a midterm, if that makes sense. Yeah. So no, again, this sort of thing. At this point, my plan for the course is, this is something that you should know for written assignments, and you should know at least how to be able to go from here to here for midterms for the final. But this sort of lengthy algebraic procedure, I'm only going to really need you to do it once. Okay. Any other questions about this? Okay. Well, this took me a little bit longer than expected, so I'm actually already about 5 minutes behind my schedule. That's okay. We've got lots of buffer time at the end, so it's not going to be a big deal. But I just noticed that. So, okay. So, where did I leave off? So I talked about displacement and distance traveled. That's the last thing I talked about last class when I was talking about the net change theorem. I've got 2 more examples, and they're basically sort of word problems that ask you either to evaluate the net change of a function or to estimate the net change of a function. So the idea is, what the net change theorem says is that you can always interpret an integral of a rate of change as the net change of that thing. Or if you want to calculate the net change, you can evaluate it by using integrals. Right? An integral is the same thing as net change. That's the idea here. The other thing to mention is we have a method of estimating the values of integrals, right? This thing called the midpoint rule. We can use that same idea to estimate the net change of a function. So if we want to evaluate the integral, we can do it using antiderivatives. If we want to estimate something, we can always do it using the midpoint rule. Cool. So here, example 9, we have a formula where water flows from the bottom of the storage tank at a rate of 200 minus 4t liters per minute. So again, this thing, 200 minus 4t, is a rate of change. It's the number of liters per minute, right? between time 0 and time 50. Here we want to find the amount of water that flows from the tank, not slows from the tank, during the first 10 minutes. So the first step in this problem is to recognize that the amount of water is the same thing as the net change. Right, so I ask for the amount of water that flows from the tank, same thing as the net change. So if I'm trying to find the amount of water that flows during the first 10 minutes, I'm trying to find the net change during the first 10 minutes. Now the first 10 minutes are time 0 to time 10. Right? That time period is the first 10 minutes. The second 10 minutes would be from time 10 to time 20, etc. Right? Now this thing here is not telling me what net change I want to find. This thing here is just telling me when is this formula valid. So sometimes it's key to sort of make sure you read the question carefully and don't use these guys as your limits of integration, because this during the first 10 minutes basically overwrites that. It's telling you we're only interested in how much the water changes between time 0 and time 10. The thing we're integrating is 200 minus 4t. So antiderivative of 200 is 200t. Antiderivative of 4t is 4t squared over 2. And we've got to do this thing from 0 to 10. So first I'm going to plug in 10. I plug in 10, I get 2,000 here. 10 squared is 100. 100 divided by 2 is 50, times 4 is 200. This gives me 1,800. Is this not recording anymore? What happened? No, it's recording? Okay. I've never seen it go to screensaver while it was recording before, and that was confusing me, but it's still recording. So 1,800 liters in the first 10 minutes. Actually, sorry, 800 liters flows in the first 10 minutes. If I ask you a question in words, I always want you to sort of answer it in words. Usually, again, there'll be 1 point of the 5 for this question. It's just putting that thing in a sentence. Explaining what it is that you've actually found. You found the amount of water that flows in the first 10 minutes. Wait. Oh, yes, sorry. Let me just show you, because I didn't actually write it out. When you plug in 0, you get 0 minus 0. And that's why I actually didn't do that part. I was like, wait, there's a step missing. And really that, again, I sort of did that in my head. And it was like, oh, it gives you 1,800. But really, again, you've got to plug in the top, plug in the bottom, and subtract. Here, when I plug in the bottom, it's just 0 for the first thing, 0 for the second. But we do still sort of have to do that step of plugging in the bottom. And the reason is because for some functions, it won't be 0 minus 0. Some functions will actually give you something when you plug in 0. Like e to the x. Plug in 0, you get 1. You don't get 0. So, okay, so last example for section 5.4 is example 10 here. Here we have the same thing, of water flowing in and out of a storage tank. Here they give you a graph of the rate of change of the volume of the water. And the idea is they want you to use that graph to estimate the amount of water in the tank 4 days later. So let me just copy that graph out onto the board. So the graph looks something like that. And I'm just going to sort of, I think that's, yeah. So 1, 2, 3, 4. Right, so the idea is, so the net change here is the same thing as the integral of this guy. Right, and we're talking about the integral from 0 to 4. Because we're talking about the net change between time 0 and time 4. The idea is that this integral is approximately the area of 4 rectangles. right? An integral is always an area. If you think about this integral as the area sort of this area above minus the area below. It's approximately the same as the area of 4 rectangles. Now here it says to use the midpoint rule. So when we draw those rectangles, we're going to use midpoints. So the midpoint of that first integral is there. Use that midpoint to draw the first rectangle. The midpoint of the second area is here. Use that to draw the second rectangle. Midpoint of this one is here. Use this to draw the third. Midpoint of this one is here. Now, if you actually look at where those are in the text, this one is at 1500. The second midpoint's at about 1800. The third one is at about 750. And that one down there is at about negative 700. Right? So if we're measuring the areas of each of these things, to measure the area, we always take the height times the width. The width of each of those is 1. So we're going to have 1500 times 1 plus 1800 times 1 plus 750 times 1 plus negative 700 times 1. So 1500 plus 750 is 2250. That's going to give you 3350. So this is approximately the net change over that time. Now the next thing to mention is it's not actually the net change they're asking you to find. What they're asking you to find here is the amount of water 4 days later. So the thing to mention is that the net change can also be interpreted as the amount in day 4 minus the amount in day 0. Right? And that change something is the amount at the end minus the amount at the beginning. We know what the amount in day 0 is. The amount in day 0 is 25,000. The net change is 3350. So I'm going to call this A4 for amount in day 4. It's an abbreviation for that. Add 25,000 to both sides, we'll get 28,350. So the amount in day 4 is 28350. So in these sorts of questions, it's important to actually read what it's asking for. Here it's not asking for the net change, it's asking for the amount 4 days later. So different things, we have different methods to calculate them. Any questions about this example? Okay, so I'm going to move on now to section 5.5. Here's the handouts for 5.5. Here's the handouts for 5.5. Take one, pass them back. So what we're going to be moving on to now, this thing is called a, so if you remember when you were doing derivatives, you learned like the chain rule, the product rule, the quotient rule, all those sorts of things. There are some rules for integration as well. And the first one we're going to learn is the substitution rule. We're not going to get into the same, for now we're not going to learn all the other ones immediately. We're actually going to do applications first before we use a lot of the other methods of integration. But the substitution rule is the one that's most commonly used, which is why we're learning it first. So, the substitution rule is going to allow you to integrate integrals like this guy. 2x sine of x squared. Yes. Now again, this is something that's complicated enough, you can't just like easily look up what the x derivative is in a table, right? It's not just sine x. It's not just 2x. It's 2x times the sine of x squared. How many people feel like they know how to integrate this thing from previous courses? A couple. How many people don't know how to do this? I've never seen it before. How many people have seen it before and forget? Okay, a bunch of those too. So the key thing with these sorts of things is, again, there's this thing called the substitution rule. Now, the substitution rule is actually the anti-chain rule. It's the opposite of the chain rule. So the idea is if you want to integrate something like this, one way of doing so is just to sort of guess and check, right? So I'm going to guess negative cosine of x squared, and I'm going to say, okay, let's check. What is the derivative of negative cosine of x squared? Well, if we take its derivative, we've got to use the chain rule. Take the derivative of negative cosine x squared. When we do that, the derivative of negative cosine is sine. Right? The derivative of cosine is negative sine. That negative sine will cancel the negative sign. So we're going to have sine of x squared times the derivative of the inside function. What's the derivative of x squared? It is 2x. So the derivative of this guy, of negative cosine x squared, is the thing inside. Right? So the antiderivative of this thing inside is negative cosine x squared. Right, maybe I should just write that on the board because I saw a couple of confused faces. So if we're doing the derivative of negative cosine x squared, right, the negative sign is going to stay. The derivative of cosine is negative sine. And then we're going to have to multiply by the derivative of x squared. Oh. Right? Negative sine x squared is sine x squared. The derivative of x squared is 2x. So, the antiderivative of this guy is negative cosine of x squared. So the question now is, how would we have made that guess, right? That is the antiderivative. Negative cosine x squared is the antiderivative of this thing. How could we ever have guessed that? Well, one way of doing it is to look at this guy and notice that there's a composition of two functions. Here we have one function inside another function, in the sine x squared part, right? But also, 2x is the derivative of that inside function, right? So if we ever see a situation where we have one function inside another one times the derivative of the inside function, that's always something that could have come from the chain rule. So whenever we have that situation where we have a derivative of something times something of the thing it's a derivative of, we can use what's called an anti-chain rule to do the antiderivative. What we do is you do the antiderivative of that outside function, do the antiderivative of sine, and keep the x squared inside. So what this says, this anti-chain rule says if you've got f of u, so f of something complicated that's not just an x, times u prime, times the derivative of that u, the integral of that will just be capital F of u. It would be you do the antiderivative of the lowercase f, apply it to the same thing inside, plus c. Because you always have to do plus c as an integral. Now the key thing to mention about this anti-chain rule is this is exactly sort of the opposite of the chain rule. The chain rule says if you have the derivative of f of u, we have like the derivative of f times u prime, if that makes sense. So if you pull out your derivative sheet that I wrote before, you will see the chain rule looks sort of very similar to this, but sort of in reverse. The key thing to mention about this anti-chain rule is that this is not the easiest way to do these integrals. This is the way that looks the most like the chain rule, but there is actually an easier way of doing these integrals, and that's what we're going to do on the next slide. And on the next slide, we're using what's called the method of substitution. Now, the method of substitution is just sort of a quick way of using the anti-chain rule. And what the method of substitution does is rather than writing like u prime times dx, we're instead going to write this symbol called du. And the reason for this is that u prime can also be written as du by dx, right? So if we have u prime times dx, that's du by dx times dx, the dx's will cancel. And that's why we use the du abbreviation for this thing. And if you rewrite that sort of rule Otherwise, the u prime and the dx will just become a du. So this rule then says the integral of f of u du is capital F of u plus c. The idea is you want to integrate a function of u, you just integrate the function as if the u was an x, and put a plus c on it. That's basically what the method of substitution says. So the way to use the method of substitution is to use these steps down here. The first thing is to find something complicated with just an x, call it u. Right? So in that example with the 2x sine x squared, we wish that x squared was just x, so we call it u. Next step is to figure out what du is. So du is always the derivative of u times dx. The third step is every time we see an x in there, try to either replace it with something that becomes u or something that becomes a du. So if we see, for example, sine of x squared in that example, that x squared inside will become a u. That 2x in front, that 2x will become the du, because u prime is 2x. Then evaluate the integral with respect to u. Do this thing, change the antiderivative with respect to u. And then replace u with whatever it is, right? U is always something in terms of x. U is something like x squared, or e to the x, something more complicated than just an x. So the final step is always to turn it back into something in terms of x. If these steps don't make much sense right now, that's okay, because they'll hopefully make a little bit more sense after I go through some examples. But any questions about this point before we move on to examples? Okay. So, here are some examples. So the first one here we want to do is the integral of e to the x cosine e to the x. So the key thing to mention is I know how to integrate cosine x, I don't know how to integrate cosine of e to the x. So I want to replace that e to the x with just an x, right? So that means I'm going to call that e to the x u. Then if I want to find du, I've got to take the derivative of e to the x, which is just e to the x, and multiply by dx. What that means is that this e to the x and the dx, those two things can become a du, and this cosine e to the x can be replaced with cosine of u. So then this will just become the integral of cosine u times du. And then if we want to integrate cosine u, we just say, okay, what's the antiderivative of cosine? It's sine. And then we put back in what u is. U is e to the x. And again, if we want to check our work, we can check it using the chain rule. What's the derivative of sine of e to the x? Well, it's going to be cosine of e to the x times the derivative of e to the x, which is e to the x cosine e to the x. So the idea is that when we're using the method of substitution, what we're doing is we're replacing an inside function with just a u in order to be able to integrate. And as we're doing so, we're getting rid of something which would have been the derivative of that u. So here we're getting rid of the e to the x. That was the derivative of the thing inside. That's the idea. Any questions about this example? Okay. Next one is example 2. Oh. Same thing happened in this example that happened in one of the ones in the last class. That 4 is, the point 4 is supposed to be up above. It's supposed to be integral of 3t plus 2 all to the 2.4. So the key thing here is that 3t plus 2 inside, I wish that was just a u, or just an x. Right? If I had x to the 2.4, that thing I can do. It's x to a power. But 3t plus 2 to a power, I can't do that. And I can't expand this. You can't expand something to a 2.4 power. If it was just 3t plus 2 squared, you could expand it and do it that way. So what we're going to have to do here is we're going to have to say that u is going to be 3t plus 2. Du, so we're going to take the derivative of 3t plus 2 is just 3 times dt. Now the problem here is I don't have a 3 times dt in this integral up here. right? So I don't have something to replace with du. But what I can do is I can divide both sides of this equation by 3. Du over 3 is dt. What that means is when I see the dt here, I can replace it with du over 3. So this integral becomes u to the 2.4 times du over 3. Now dividing by 3 is the same thing as multiplying by 1/3. So we can also write the integral this way. 1/3 u to the 2.4 du. And now this should be easy. It should be easy to see how you integrate this. Integral of u to the 2.4 is u to the 3.4 over 3.4. Right? You add 1 to the exponent, divide by the new exponent. Plus c, 3 times 3.4 is 10.2, and u is 3t plus 2. So we get that. 3t plus 2 to the 2.4 over 10.2 plus c. Yes?
3.4.
Oh, thank you. Thank you. Any questions about example 2 here? Great. Okay. So example 3. Oh. Integral sign missing here. This was example 1. This is example 2. I'm going to redo example 3 back to the same place as example 1. Here we have the integral of z squared over z cubed plus 1. So the key thing here, I don't actually see a composition of two functions here. I don't see one function inside another. But what I do see is a fraction. And fractions are annoying things to integrate because we don't have a quotient rule for integrals. And again, I've done some fractions before if it was just a z on the bottom. Right? It was just a z on the bottom, I could do z squared divided by z. That would be z, just z, right? Because it's z cubed plus 1 on the bottom, I can't do it that way. And so usually if you have something complicated like that on the bottom, the easiest way to do it is to do substitution. To say u is whatever that thing on the bottom is. In this case, u is z cubed plus 1. Right? I wish that thing on the bottom was just a z, because then I could just divide. So I'm going to call it u. So if u is z cubed plus 1, du, I'm going to do the derivative of u, which is 3z squared times dz. Now, if you'll notice, I don't have a 3z squared here. What I have is just a z squared. Right? So I'm going to divide both sides of this by 3. Du over 3 is going to be z squared dz. So then this integral will become the integral of 1 over u, right? This thing is basically a u on the bottom, times du over 3. Right? This is basically 1 over z cubed plus 1 times z squared dz. That's another way of thinking about that. That becomes 1 over u times du over 3. And then I've got to integrate. So first I'm going to take, okay, dividing by 3 is the same thing as multiplying by 1/3. And a constant can always come out front of the integral sign. I haven't done many of these things yet, but I did mention that that's a rule, that if you have a constant inside the integral, you can always move it out front. Constant times something. The integral of 1 over u, the antiderivative of 1 over u, is ln of the absolute value of u. And u here is z cubed plus 1. the x derivative is 1/3. Yes?
Quick question, when you're taking out a constant like 1/3 like that, does that affect C? Like, would you say that C is 1/3 of the C1 of?
It doesn't matter, because C could be anything.
Right.
Right, so
Okay.
if C, yes, you can.
I've just noticed that the textbook sometimes like clarifies that the constant is C1.
Yeah, just
and
like this,
1/3.
yeah.
So I was just wondering if you're going to be.
I usually gloss over that,
Okay.
because it doesn't matter, because, okay, for example, yeah, and I just tack on a plus C on the end once I'm completely done. There are some situations where it matters what C is, and those situations are when we're dealing with differential equations, and I'll be like at the end of the course, and I will sort of talk about what specifically to do in those situations, but really, yeah, it doesn't, at this point, it doesn't matter. Yeah, just tack on a plus. And again, technically, yeah, you could put brackets here, and then you could do C times 1/3 is 1/3 C, and well, C is a constant, and 1/3 C is also a constant, let's call it C1. Right? You can, that's totally allowed, you're allowed to do that. Usually I just do whatever the thing is, tack on a plus C on the end, it's always going to be correct that way. So, yeah. And if you didn't understand that, that's okay. It's perfectly fine to be able to do that without understanding why there's a difference between a C and a C1. Any, oh, now example 3. I'm lightning through classes today. Any other questions? Okay. So the next thing I'm going to mention is some guidelines for telling you when to use substitution and how to pick what U is. Usually the hardest thing with the substitution problem is figuring out what U should be, what to pick to be your U. Once you've gotten that part, the rest of it is just doing a derivative, doing some algebra, you're finding a simple antiderivative, plugging in the x, right? The rest of it's mostly just algebra after you figure out what U is. But sometimes, in complicated questions, it's hard to figure out what you should pick to be your U. So I have 3 guidelines that are useful for doing this. So the first guideline says if you have a composition of 2 functions, if you have one function inside another function, pick U to be your inside function. So here we have this integral here, the integral of 3x e to the x squared plus 4 dx. Here, the x squared plus 4 is your inside function. So that's why we're going to let our U be x squared plus 4 in that example. If we have a fraction, you should oftentimes pick U to be the bottom of the fraction. So we have an integral like this, integral of y to the 5th over y cubed minus 3 dy. We're going to pick our U to be the bottom of that fraction. Now there are also some situations which don't fit either of these examples. That don't have a composition of 2 functions, don't necessarily have, well, they have a fraction, but you can't necessarily make U be the bottom of the fraction and have it work out. And here's an example of one where that doesn't work. Here you have 1 over 1 plus x times 1 over square root of x. We have actually a product of 2 different fractions. And the key thing, it turns out that what works in this situation is actually picking U to be square root of x. And the reason that works is because the derivative of square root of x, square root of x is x to the 1/2, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. X to the negative 1/2 is this thing, 1 over square root of x. And this 1 over square root of x is going to be, if you try to do this integral any other way, it's this 1 over square root of x which is going to be screwing you up every single time. So you can actually get rid of the 1 over square root of x by making it become the du. By picking your U such that this part will become the du. And this sort of last method is usually a method of last resort. If you can't figure out any other way of doing it, try using this approach. It'll usually work. 90% of the problems will be one of the first 2 methods. But there are sort of those 10%, the hard substitution problems, where you have to think a little bit more creatively when picking what U should be. And at the times you're thinking more creatively like that, really what you've got to think of is, okay, what is the most thing that's screwing me up the most? Is that the derivative of something? And if the thing that's screwing you up is the derivative of something, pick your U, so that thing that's screwing you up will become your U. Any questions about these guidelines before I go on to some examples using them? Okay, so got 3 more examples, one for each of those guidelines, I believe. Okay. I'm starting off with example 4. So here we have the integral of 2 to the t over 2 to the t plus 3. Right? The key thing here, there's no composition of functions. We don't have one function inside another function, but we do have a fraction. Right? And so we want to pick u to be whatever's on the bottom of the fraction. So I'm going to pick my u to be 2 to the t plus 3. That looks like an m. Then, if I find du, I'm going to take the derivative of this. The derivative of 2 to the t is 2 to the t ln 2. And then I tack on dt, right? The du is always the derivative times dt. Now I don't have this thing up here. What I have is a 2 to the t dt. So I'm going to divide both sides of this by ln 2. So du over ln 2 is going to be 2 to the t dt. So then this integral is going to become the integral of 1 over u du over ln 2. Right? This is basically 1 over 2 to the t plus 3 times 2 to the t dt. So the 1 over 2 to the t plus 3 is 1 over u. The 2 to the t dt is dt over ln 2. The ln 2 here is a constant, so I can pull a 1 over ln 2 out front. Right? There's no t's, there's no u's in this thing. That's why it makes it a constant. It's an ugly constant, but it is just a constant. Integral of 1 over u is ln absolute value of u. And u here is 2 to the t plus 3. Any questions about example 4? Okay. So example 5. So here, example 5 is integral of x over 1 plus x to the 4 dx. Now, what I'm going to do first is I'm going to say, okay, there's a fraction. I want to pick u to be whatever's on the bottom of the fraction. So du is going to be 4x cubed dx. And let's see what's going on if I did it this way. Well, if I did it this way, I've got an x dx here, right? And I have a 4x cubed dx. So I could have tried dividing both sides of this by 4x squared. So du over 4x squared equals x dx. And then if I did it this way, this integral would become 1 over u times du over 4x squared. And now we're faced with our problem. And the problem is that 4x squared is not a constant. So I can't pull it out front and get rid of it. And if I have an integral with both u's and x's in it, it's going to be impossible to do. You cannot find an antiderivative of something which has two different variables, a u and an x, or a y and an x, or two different variables that aren't constants. So it turns out if you ever get something like this, where we've got u's and x's, I can't figure out any way of getting rid of those x's, I've probably picked the wrong u to start off with. So I say, okay. So I'm going to go back to the beginning and try a different approach. All right, so let me... So this is the wrong u. Well, if I try a different approach, one way I can try this different approach is to look at, rather than look at what's on the bottom, actually look at this thing. X dx, right? And I want to pick something such that that thing will be my du. Right? That's sort of that third approach, that approach of last resort, if the other two don't work. And so what I'm actually going to pick here is I'm actually going to pick u equals x squared. Then my du will be 2x dx, and what I really have is an x dx. I can divide both sides by 2. So the x dx will become a du over 2. And if I do that, what will happen is because u is x squared, this x to the fourth I could think of as x squared squared. So that x to the fourth will actually become a u squared. Again, this 2 now is a constant. I can pull it out front. And 1 over 1 plus u squared, that's an integral we know how to do. That's tan inverse, or arctan. So that's the idea here, is that sometimes our first approach might lead you to pick the wrong u. And if the first approach doesn't work, then try a different approach. And oftentimes when you're trying a different approach, that's when you sort of have to look at that last guideline I showed you. That says, look for something that's really causing you problems and make that thing be the du. Pick the u, so the du will turn out to be nice. The du will turn out to be x dx. And then just recognize, okay, if u is x squared, the x to the fourth will actually become a u squared. Then that will be something we know how to do. Any questions about example 5 here? Yes?
I'm kind of confused how you got x squared again.
How I got x squared? I looked at this thing, this x dx. And I said, I want that to be my du. I want that to be my derivative. What has x as its derivative? Well, x squared has 2x as its derivative, which is pretty close to x, right? I could also pick u equals 1/2 x squared if I really wanted to. That would just have these extra 1/2s floating around that would cause more harm than good. But I'm picking it u to be x squared because, again, it has a derivative that's very similar to what I've got here.
So I don't necessarily have to take exactly that x then. I should look at what the derivative is of that.
I should look at what has something that looks like this as its derivative. Yeah, what has something that looks like this as its derivative? X squared has 2x as its derivative, which looks a little bit like x. Right? And try it and see if it works. And again, a lot of it, these problems are going to be a lot of trial and error. Some of the harder substitution problems, you might have to try 3 or 4 different u's before you get one that works. Now, once you've worked on them and once you've practiced them, oftentimes you can get a hang of which ones have to work in which situations. But yeah, sometimes it requires a fair bit of trial and error before you get to that place. So the last example I'm going to do is example 6 here. So here we have the integral of x cubed square root x squared plus 1 dx. So here we have a composition of 2 functions. We have one function inside another function. Whenever we have a composition of 2 functions, the u we should always try will be the inside function. Our du will then be 2x dx, right? The derivative of x squared plus 1 is 2x. Now what we don't have, so we have here an x cubed dx. So I'm first going to divide both sides by 2. And then I'm going to multiply both sides by x squared. And so x squared du over 2 is x cubed dx. So great, I know what the x cubed dx is going to become. It's going to become x squared du over 2. So when I do that, I will get x squared du over 2, and the square root of x squared plus 1 will become the square root of u. Now this is one of these integrals where now I have both x's and u's. And again, I said if you've got both x's and u's, you can't integrate. But I can do something to take this thing and turn it into something involving u. U is x squared minus 1, which means x squared is u minus 1. Oh, u minus 1. U is x squared plus 1, so x squared is u minus 1. So, and then over 2 can become a 1/2 out front. So I get that thing. The 1/2 can come out front, x squared can become u minus 1. Square root of u is just square root of u. Now, square root of u is the same thing as u to the 1/2. U times u to the 1/2 is u to the 3/2. I'm adding exponents. This is a u to the 1, it's a u to the 1/2. 1 plus a half is 3/2. 1 times square root of u is u to the 1/2. Again, all I'm doing is I've got something times something else, so I'm expanding it. I'm going to erase this. I see some people straining to see, so I'm going to just continue over on this last column. If we want to integrate u to the 3/2, it's going to be u to the 5/2 over 5/2. If I want to integrate u to the 1/2, it's going to be u to the 3/2 over 3/2. Tack on the plus c. Oh, the 1/2 is multiplied by the whole thing. And u is x squared plus 1. So dividing by 5/2 is the same thing as multiplying by 2/5. The u will become x squared plus 1. So that's the final answer. 1/2 times 2/5 x squared plus 1 to the 5/2 minus 2/3 x squared plus 1 to the 3/2. Bracket plus c. So again, this final answer is fairly lengthy here. Any questions about example 6 here? Again, this is an example of a situation where I definitely do not want you to try to simplify this thing. You can simplify it, but it's not worth the effort. Just leave it like this.
I'd at least get rid of the fractions, because your half gets rid of
Yeah,
the 2's on
it'll get rid of these 2's and the fractions, exactly.
Looks nicer.
Yeah. No, yeah, exactly. And I definitely, it'll make me happy if you do, but I know sometimes people will get things like this and be like scared of how complicated it is. And if you get that situation, just leave it. I'll mark it as correct, as long as it is correct. Like simplifying, again, is a nice thing to do, but in things that become this complicated in the end, I'm not going to be testing you on that ability. Okay, so I'm, again, about 15 minutes behind my schedule now rather than just 10, so hopefully I won't cause too much of a problem later, but take a 10-minute break. Take a break until 5 minutes to 1. What else was I going to say before? Oh, no, sorry, what quizzes to hand back? So, Dimitri, did you sign up for WebAssign yet?
I did.
Great. I will, over the break, I will enter, actually, no, I know what your grade is. I'll enter into WebAssign. Anyway, you were the one person who hadn't signed up on Tuesday, so thanks. Yeah. Mike. Mike here? No. Parmbeer. Sam. Dave. There we go. Sunny. Ellen. Clement Baines. Kyle. Alicia. Harleen. We've got new people next. Dylan. Colin. Joshua. Chikatlo. There we go. Justin. Ryan. Oh, we have 2 different Ryans. Ryan Sheehan. Yes, we have a Ryan. Yes. I was like, no, I didn't think we had 2 different Ryans. Yeah. Nimrat. Interpreet. Maya. Avi. Yeah. It looks like an AU for some reason. I was like, oh. Karanjeet. And Daryl. there you are. Michelle and Joe and Brian and Jackson. Oh, there you go. And Katrina, Kate, and Brandon,
I know, it looks like that too.
and Anvir, and Katie, and Danielle. Okay, yeah, if you have any questions about the quiz, your marks on the quiz, whatever, feel free to come ask me. Oh, I need to print off those assignments.
Can we just go over this one? Because I got this answer because I put in the calculator, but I don't know how to get the midpoint.
I didn't ask you before. I
Or
said left
left.
endpoint.
So how do you like?
The left endpoint of this one is 0. This one is 0.5. So the first one, the left edge of the first one is 0.
So you just go all the way up until it touches and go.
Well, just no, you don't go left. You measure the height at 0.
Yeah.
What formula do you use to measure the height? This formula. So you do
Okay.
4 minus 0 squared.
Okay.
So the height, the left endpoint is 4.
I see.
The left endpoint of the second one is 0.5. So you measure the height using this
0.5.
formula, 4 minus 0.5 squared.
Oh, I see.
Left endpoint of this one is 1. 4 minus 1 squared.
And if it was right endpoint?
Then you'd use 0.5, 1, 1.5, and 2. Right, because the first one, the right endpoint is 0.5.
Oh, I see.
Right endpoint is 1. Right endpoint is
Okay.
1.5, 1.2.
And if it's middle?
If it's midpoint, then you'd measure 0.25, 0.75, 1.25, 1.75.
I see. Okay. Thanks.
Yeah.
I don't know what is wrong here.
Do you just put a plus instead of a minus?
It is a minus.
And if you look underneath, there was a plus. I should have written it above or below.
It was a minus.
There was totally a...
I think for this one, it was, remember you said we can't do something negative?
Yeah, but this is below. That's why it's negative, because it's below. And you can't have something negative if it's above. This graph is not above.
Oh, okay. So
So it has to be negative. Because the idea is you take the bigger one minus the smaller one. Which of these is bigger? This one is bigger because it goes from 0 to 6. Right? This is bigger than this. The bigger one minus the smaller one. Which is 3 minus 5. Right? Yeah. Yeah.
I just grabbed the test.
Oh, yes.
So Mike.
Mike. There we go. There we go.
Perfect.
So right on top.
Thank
I know, I was looking down below and I couldn't find it. Yes.
Just a question, with oscillated, where'd you get U minus 1?
U is x squared plus 1. Move 1 to the other side, so x squared is u minus 1.
Oh, okay.
Yeah.
May I ask for the web assign?
Yes.
Is that really that you deduct a mark for the second answer? For
Yes.
25%?
25%, yeah.
I just typed the wrong answer for 2
Yeah.
times and
Just
finally get
try to be careful about what you type in the first time. That's the only thing I can say is that, like, yeah. Yeah. I can't really make exceptions because it applies to everyone, and then if I make the exceptions, then I'm grading you in a different set than grading everyone else. So.
It's
Yeah.
2 times. So, when I 111, it haven't deducted there maybe
Yeah.
three times.
Yeah.
So,
Yeah, and again, different classes have different policies. That just is the policy for this class, so it's like, yeah. Yeah. So yeah, the key thing is make sure, check your answer before you type it in. The key thing is I want to discourage people from guessing. That's what I want. Because some of them are multiple choice. And if I gave, right?
yeah,
and-
multiple choice to be the
Exactly.
only one.
And now the key thing is, the problem is I don't have a way of changing the grading
Chance.
criteria for the multiple choice ones and for the non-multiple choice ones.
We can ask Ben. I think he know how to do it.
Yeah.
Ben, yeah, he was my teacher.
Yeah.
111.
Yeah, I was
I
gonna say,
think-
I only know how to change the, like, grading criteria for the assignment as a whole, so maybe there's a, yeah.
For multiple choice, he only give us 1 chance, but
Okay.
others I think
There's
it's
more than
3.
one.
Yeah.
Okay. Yeah, I mean, I can go through and try to see if I can do that, but I don't, yeah.
Didn't you have to go get something?
Oh, yes, the quizzes, the quiz, the assignments, thank you. I am Yeah, which means we're not going to be starting at the time I said we would start. Oh, never mind. I can't actually print from this computer. Okay, it will not. I will have to do it after class, and because I'd have to run up to my office, plug the USB key to my, start at the computer in my office, plug the USB
You
key.
can
and
just
put it in
email
there.
them to us, can't
Yeah,
you?
exactly. No, it's going to be on the course web page anyways.
Alright.
So yeah, yeah. And I will. So yeah, I'll have to class. I'm going to do it through the course web page right now, so I don't forget.
How much are the web assigned quizzes weighted?
10% of them are for all of them together. So there's going to be like 13-ish of them. So that's like less than 1% each.
See the website, prison my kids, and I'm like,
Okay, so I'm just going to mention that I actually can't print from this computer, so I will have to print off the assignment after class. So if folks want to come by my office at like 2 o'clock, I will have these printed off, or come by Math. I'll be the Math Center till 4, or Math Center for 2:30 to 4 today. So if you want to copy the assignment printed, you can do that. Otherwise, you can just go into your course homepage, download it, open it up, and it looks like this. It's one question with 5 parts. You got an integral, and basically I'm asking you to do it 4 different ways and compare your answers. Yeah, anyway, so I just wanted to mention that this is what the assignment looks like. Again, you don't have to hand in this sheet of paper, this is just a question paper. As long as you, one question, 5 parts. And yeah, you can get that off the course web page, or I will also print them after class today. If you want to come by my office today to grab them, or by the Math Center after 2:30, I can get one to you. Otherwise, I'll have them again on Tuesday. Okay.
Can we find it online?
You can find it online, yes. So if you go back, right,
And we
course
need to
web
hand in.
page, files, assignments. Yes.
We need to hand in the front page.
You don't have to.
So
Just put your
only
name
a
on it, and
sheet of paper.
yeah. Put it on a sheet of paper, write assignment 1 on the top, put your name, hand it in.
Oh, okay.
So no, you do not need to hand in that page. As long as your name, the words assignment 1 are on there, it'll be fine. Yeah. Okay. So I'm going to go back to where we left off. Okay. So I don't know if you noticed this, but all the examples I've done so far have all been indefinite integrals, right? There have been no limits of integration. So the next thing we're going to need to do is sort of apply the methods we've learned to definite integrals, situations where there are limits of integration. And so again, here's an example question we can do with substitution. And this one now is a definite integral. We have limits of integration here. How many people here feel like they remember how to do this sort of thing, or they feel like they can do it easily now that they've seen the indefinite integrals? How many people don't feel like they can do this at all? Okay. I mean, again, yeah. So, the key things, when there are limits of integration, there's actually 2 different ways of approaching this sort of problem. And I'm going to talk about both of them. Both of them are valid. I prefer the second way, but because it's a little bit faster, but both are valid. So there's 2 methods of doing definite integral substitution. One way is to just forget about the limits of integration for the time being, do it as if it's an indefinite integral, find the antiderivative, and then put the limits of integration back on at the end of the question. Right? So that's sort of a method I was doing definite integrals last class. If you remember when the section 5.4 in indefinite integrals, I said, look, let's show you how you can apply this method of indefinite integrals to definite integrals. That's sort of one way of doing these things with substitution. The second way of doing them is what's called changing the limits of integration. So the idea is when you do substitution, you take something which is an integral with respect to x, an integral dx, and you turn it into an integral with respect to u, an integral du. Now here, these limits of integration tell you what the smallest x value is and what the biggest x value is. We can actually, what we can do is we can figure out on this integral what the smallest u value is and what the biggest u value is. And if we do that, that will actually make it easier to do that limit of integration then, to do that integral. And the reason is because once we get to this step, we don't need to put a plus c on the end. All we need to do is put the u limits integration, plug in the values of u into here. We don't even need to do this last step of putting it back in terms of x. If we change limits of integration, we do not need to do this last step, where we put everything back in terms of x. That's the idea. So I'm going to do this example here, the integral from 0 to 1, x e to the negative x squared dx, and I'm going to do it in two different ways. So the first way I'm going to do it is I'm going to start by doing the indefinite integral, right? Take off the limits of integration, do it like this. So u is negative x squared, right? That's the inside function here. Du is going to be negative 2x dx. Divide both sides by negative 2 because we have an x dx here. X dx is going to become du over negative 2. So this will become the integral of e to the u du over negative 2. Dividing by negative 2 is the same thing as multiplying by negative 1/2. And then the integral of e to the u is just e to the u, right? The antiderivative of e to the u is e to the u. Tack on a plus c, plug back in what u is. And then I've done the indefinite integral. Now I've got to put those limits of integration on. And now I can plug in the limits of integration. So negative 1/2 e to the negative 1 squared minus negative 1/2 e to the negative 0 squared. This is negative 1/2 negative 1 squared is 1 plus 1/2 e to the 0 is 1. So it's negative 1/2 e plus 1/2. So the idea is that this is sort of one way of doing a definite integral using substitutions. Take the definite integral, turn it into an indefinite integral, forget about the limits of integration, do substitution, put the limits of integration back on, get your answer. This turns out to be the long way of doing. So firstly, are there any questions about how I did this example that way? Okay. So the next thing I'm going to mention again is this is the long way of doing it. There is a shorter way of doing it. And the shortcut is, firstly, we're going to do the same substitution. We're going to take u to be negative x squared. So du is negative 2x dx. So du over 2 is, du over negative 2 is x dx, right? And then what I'm going to do is I'm going to change these limits of integration. When x is 0, u is negative x squared. So when x is 0, u is negative 0 squared, which is 0. When x is 1, at the upper limit of integration, u is negative 1 squared. 1 squared is 1. The negative of 1 is negative 1. So what we're going to do is when we write out this integral in terms of u, which is going to be the integral of e to the u du over negative 2, what we're going to do is we're going to put the new limits of integration on. When x is 0, u is 0. When x is 1, mu is negative 1. Yes?
Isn't negative 1 squared 1?
It's not this. It's not negative x all squared. It's the negative of x squared.
Oh, okay.
Or, sorry, maybe I should put the squared inside here to make it more clear. You square it first, then put the negative on. One thing to mention is sometimes when we do this with substitution, we'll get an upper limit that's actually smaller than the lower limit. What that tells you, if you get an upper limit smaller than the lower limit, is you're probably going to get a negative answer, because you're integrating backwards. And if you remember, if I switch the limits of integration to put them in the right order, I put a negative sign in front. That's all that's really telling me. So then, to integrate this, I can pull a negative 1/2 out front. Right? The x derivative of e to the u is just e to the u. And then I plug in 1, plug in 0, and subtract. E to the 1 is e, e to the 0 is 1. And you'll notice, negative 1/2 times e minus 1 is the same number as negative 1/2 e plus a half. Yes? Oh, yes. Wait a second. Then why is... Oh. Okay, thank you. That is supposed to be e to the negative 1. That is supposed to be e to the negative 1. This, I made a mistake over here. Here it is the negative of 1 squared again. It's not negative 1 all squared. So this is supposed to be e to the negative 1. This is supposed to be e to the negative 1. There we go. Thank you. I was too concentrated on trying to get the same answer as I did before. And I messed up that negative 1 squared before. So again, you'll notice that the second method I did this example, I only took 2 columns of the board rather than 3. A little bit faster. It's not a lot faster, but it is a little bit faster. Any questions at this point? Okay. So, I've got 3 more examples of definite intervals that I can do substitution. Just showing you what happens in these sorts of situations. So the next one here is example 8. Here we have the integral from 0 to 4, x over square root 1 plus 2x dx. So, here we have a function inside another function. We have something inside a square root. That tells me we need to do the substitution, u equals 1 plus 2x. It's going to be the only way of dealing with that thing inside a square root. In that case, du is going to be 2 dx. Take the derivative. That's what I get my du to be. Now here I don't have a 2 dx, I have an x dx. So let me just rearrange this. Du over 2 is dx. So actually I'm just going to turn this dx into a du over 2. I'm not even going to, if you wanted to, you can multiply both sides by x and say you can turn the x dx into an x du over 2. You don't even need to. You can just replace the dx with du over 2. The other thing we need to do is we need to change those limits of integration. So the lower limit, we say when x is 0, u is 1 plus 2x, which is 1 plus 2 times 0, which is 1. When x is 4, u is 1 plus 2 times 4. 2 times 4 is 8. 8 plus 1 is 9. So, when we write this out again, it'll become the integral from 1 to 9. Right, those are your new u limits of integration. X over square root of u du over 2. Now, you'll notice I still have a problem here, right, which is that I still have an x. Well, the idea here, I'm just going to finish erasing this so I have more space to use. The idea here is that because u is 1 plus 2x, u minus 1 is 2x, so u minus 1 over 2 is x. So that x there I can replace for u minus 1 over 2. Or you pull this 1/2 out here. This division by 2 here is equivalent to pulling another 1/2 out front. So I can write it as a quarter, u minus 1 over square root of u. And then here I've got u over square root of u and 1 over square root of u. U over square root of u will become u to the 1/2. 1 over square root of u will become u to the negative 1/2. And then I'm going to integrate. The antiderivative of u to the 1/2 is u to the 3 over 2 over 3 over 2. The antiderivative of u to the negative 1/2 is u to the 1/2 over 1/2. This goes from 1 to 9. And I'm just going to plug in the 9, plug in the 1, and subtract. Divided by 3 over 2 is the same as multiplying by 2/3. 9 to the 3 over 2 is 27. 9 to the 1/2 is 3. Oh, great. I'm going to put close brackets there. And then when I plug in 1, 1 to the 3 over 1/2 is 2/3. That'll become a 2/3 minus 2. When I plug in 1. 27 over 3 is 9. 9 minus 6 is 3. 2/3 minus 2 is negative 4/3. Take the negative of that becomes plus 4/3. And this 3 plus 4/3 is 9 plus 4, which is 13/3, times a quarter is 13 over 12. So you'll notice that one thing that this method of doing the integral saves is I didn't have to put back in 1 plus 2x for u in this case. And that saved me a fair bit of time in getting my final answer. Again, I oftentimes skip some steps in sort of this calculator portion and do it really quickly. And the main reason is because, again, it is just at that point just using a calculator. Any questions about what happened there?
Yeah, what is that?
Which 3? This 3? 2/3. Oh, yeah. This is 2/3 times 27. 9 times 2 is 18 minus 6. Thank you. It's a 12. So 2/3 of 27 is 18. 18 minus this is 6 is 12. What happens when I cut corners? 40. Which reduces to 10 over 3. Okay. I'm going to do 2 more examples and go to group problems. The reason is that I'm realizing I don't have enough time to actually get through 5.5.3 today. 5.5.3 is fairly straightforward. I'll end up doing it on Tuesday's class. Okay. So example 9. Here we have the integral from 0 to 1/2 sine inverse x over square root 1 minus x squared dx. Now this example, if we try doing u equals 1 minus x squared, we will not be able to get anywhere. If we try doing u equals the whole thing on the bottom, we will also not be able to get anywhere. The key thing in order to actually make this integral work is to notice that this is sine inverse of x times 1 over square root of 1 minus x squared. And this thing here is actually the derivative of sine inverse x. So to do this integral, we have to use that sort of a last guideline I talked about. Is if there's something there that's really annoying that's causing you problems, is it the derivative of something? It is. This thing here is actually the derivative of sine inverse. So I'm actually going to pick my u to be sine inverse of x, because its derivative is 1 over square root of 1 minus x squared. So the idea is that this whole thing here will become a du. That will just become u. It shouldn't be too hard to do. Yes? U equals 1 minus x squared. What? Okay, if you do u equals 1 minus x squared, the derivative is 2x. Negative 2x. There's no negative 2x for me to pick up. Oh, u is sine inverse of x, or u equals the square root of that thing? So u equals this thing. Its derivative is going to be very complicated. It's not going to be sine inverse. If you pick u to be this thing, what's the derivative of that thing? Well, you need the quotient rule to do the derivative. The quotient rule and the chain rule to do that derivative. It's going to be a really ugly, annoying derivative, and we're not going to be able to find this anywhere in here, right? Because this guy is the derivative of this guy. You want to pick u to be this guy, and this one turns out to be the derivative, not the other way around. You pick u to be this guy does not turn out to be the derivative. Does that make sense? Yeah. You always want to pick u to be the thing that has the other thing as its derivative. So the next thing to do is to change those limits of integration. So when x is 0, u is sine inverse of x, so u is sine inverse of 0. What's sine inverse of 0? It's just 0. When x is 1/2, u is sine inverse of 1/2. Now, if we want to figure out which angle has sine equal to 1/2, that angle turns out to be pi over 6. Again, that's one of your special angles. So the integral will become the integral from 0 to pi over 6 of u du. The antiderivative of u is u squared over 2. And we've just got to do this from 0 to pi over 6. So we plug in pi over 6. We have pi over 6 squared over 2. We plug in 0. We have 0 squared over 2. Pi over 6 squared is pi squared over 36. Dividing it by 2 gives you pi squared over 72. And that's the answer, pi squared over 72. One thing to mention again is, in this course, we always prefer exact answers. Like pi squared over 72 is the exact answer. We don't want you to type this into your calculator and get an ugly decimal. Pi squared over 72 is more exact. It hasn't been rounded off at all. It's easier to write, save space. Everything is better about that. Sorry, it's a 72. I don't know if that line was from before I erased it. Any questions about this example? Okay. So example 10 is this one. Integral from 0 to capital T over 2 sine 2 pi t over capital T minus alpha dt. Now, one thing to mention about this integral is this integral is unlike any integrals I've done before because there are unknown constants in the integral sign. So I don't know if you remember from Calculus 1 that you probably did some derivatives that have like these like a's or b's floating around, right? Those were unknown constants. Same thing is happening here. This capital T and this alpha are both constants. The numbers, we just don't know what those numbers are. But they're not variables. They aren't changing. They are unknown, but they're fixed. So when we take the derivative, we have to remember to treat them as constants when taking that derivative. We treat them as if they were just a pi or an e. or a 2, or a 7. We don't have to use, for example, we don't use quotient rule to do this. This t on the bottom is just a constant. So, here, the ugly thing that's giving me problems is this thing inside the sign. So substitution we're going to use is u equals sign, or no, u equals, sorry, 2 pi t over lower capital T minus alpha. Now if we find du, we've got to take the derivative of that thing. The thing to mention is because we're integrating with respect to lowercase t is the variable here. Everything else is a constant. So we take the derivative of this thing we just think of as 2 pi over capital T all times lowercase t. So the derivative of that is going to be 2 pi over capital T. The derivative of alpha is just 0, because alpha is a constant. So then we don't have a 2 pi over capital T dt, we just have a dt. Multiply both sides by 2 pi over capital T. We get t over 2 pi du equals dt. Now we need to change those limits of integration. So when x, or t, for lowercase t, is 0, what is u? Well, we're going to plug 0 into this formula. This gives you 0 minus alpha, right? So when t is 0, u is negative alpha. When t is capital T over 2, we've got to take a capital T over 2 and plug it into this formula. In that case, my u will be 2 pi capital T over 2, or let's write it this way, T2, right? We're basically plugging in a capital T over 2 in here. Here the capital T's will cancel, the 2's will cancel. So u is just going to be pi minus alpha in that situation. So the new integral here will be the integral from negative alpha to pi minus alpha sine u and dt will become capital T over 2 pi du. And again, the key thing to mention here is capital T is just a constant, so we can pull this whole thing out front. So we get capital T over 2 pi, integral from negative alpha to pi minus alpha, sine u du. The antiderivative of sine is negative cosine. So we have capital T over 2 pi, negative cosine u, from negative alpha to pi minus alpha. And so it's going to be capital T over 2 pi, negative cosine pi minus alpha, plus cosine negative alpha. And again, the reason this is a plus is because usually it's this minus this, and that negative sign, those two negative signs will make a plus. And that's what you get for the integral. And again, this is a number, it's a constant, we just don't know what number it is until we know what capital T is and what alpha is. So that's, yeah, okay, so anyways, I'm definitely 10 minutes-ish behind where I wanted to be. I am going to, at this point, sort of stop. I'm going to do 5.5.3 in Tuesday's class. I think when I was scheduling today's class, I forgot how long this stuff sometimes takes to go through. One thing to mention about some of these examples that I'm doing is these examples have been specifically hard examples that I've been doing. The last couple ones at least. The first 4 or so were like sort of straightforward-ish. I've specifically been doing a bunch of hard examples at the end just to sort of show you how the hard ones look. Don't be discouraged by these guys. Definitely try the easier ones first. The easier ones might turn out to be a breeze for you. In that case, then you just can start looking at these guys. Yeah, I'm not going to do 5.5.3 today. I am going to give you some group problems. Now, one thing to mention, again, number 1 on this slide was actually the one I gave you last class. Oh, shoot. Okay. This is the first one. I put it on that slide. So I'm actually just going to write them on the board, because I can't have them both on the slide at once. So the first group problem is this guy. Do that integral. Tan inverse of x over 1 plus x squared dx. The second one is, that one I already did as an example, number 2 on there. That's also a mistake. Let me pull out a second one to give you, you know what, just do this guy and do numbers 3, do that guy and do number 3. Because we don't have as much time to go group problems as I've intended. So I think if we do those, if you try this one, and you try number 3 on there, that should be a good review of everything. So this is number 1, and number 3 is if f of x is the slope of a trail at a distance of x, what does the integral from 3 to 5 f of x dx represent? And again, please talk about these with your groups. Specifically number 3. I think it's one of these ones some people will see it and other people won't, and definitely, consulting with your group members on it will definitely, hopefully help. And you have to work on these for about 10 minutes. At 1:35, I will show you what the solutions to these guys are. And if you get through both of those, you can try number 4 here. Number 2 I already did as an example, so you don't have to worry about that one. But try number 4 if you get through both number 1 and number 3. Yes?
Just had a question about one of the examples. So I get the whole U part.
Yeah.
I'm just wondering what happens to the 1 over square root of 1 minus x.
That becomes your du. 1 over square root of 1 minus x squared dx. That becomes your du. This would be du, not dx.
Oh, okay.
Yeah, if you have a u and a dx, you can't integrate. But if you have a u and a du, you can.
Right,
So that's the
okay.
idea. If it's mixed, you can't integrate it.
Because we're using U to substitute for sine.
Sine inverse will become the u.
Yeah.
The 1 over square root minus u squared of the dx will all together become the du.
Oh, and then that's why you get U
And
times
that
du.
change the slope. Yeah, it would be the
Okay, it all makes sense now.
Yeah.
Thank you.
That's great.
3 miles through the body.